Alright, so we're going to start out this video talking about gas laws. And so there's the property of pressure, temperature, volume of the gas, or the volume that the gas is occupying, and then the number of moles of gas, the number of particles of gas that there are. And so all of these are related. So if we change one, other properties will follow suit and change as well. And so I will point out, maybe this stuff seems obvious if you've worked with gases before, maybe not. And you might think also when I go through these laws, and then we'll combine it into the combined ideal gas law at the end there, that they would have had a little more overlap in the time they were working. Like, it was a decade or two. I was like, no, this is over 100 years of work. These guys just kind of handed the torch one to the next. Like, they really spent a lot of time really looking at like one specific relationship of gases. So Amotin got a law named after him. Thus it's called Amotin's law. And so he looked at pressure and temperature. Okay? If you heat up a gas, what happens to the pressure? So you have it in a fixed container. So you have it like in a solid, iron container or something like that. Not a balloon, nothing flexible. Like the volume is fixed. We're not putting more gas in or taking gas out, so the amount of gas in the container is fixed, and then you just put a candle under it or whatever and heat it up. And you have a little pressure gauge and you see what happens. And so what Amotin found was that as we increase temperature, pressure goes up as well. Alright? This is life work right here. This was life work. Don't make fun of it. So, what that means is that temperature and pressure are directly proportional. So that means proportional. It's a Greek alpha, but if you use it in place of an equal sign, it means they're proportional. So maybe, doubling the temperature doubles the pressure, maybe not. But anyway, as one goes up, the other goes up. That's what we're saying. So the same thing as they put up here, just a fancier way of writing it. And so when he did these experiments, it was a fixed volume, like I said, and fixed number of gas particles as well. So it was really isolating variables. So he allowed pressure to change and he allowed temperature to change. But he didn't change the volume of the container. So he had a solid walled container, did not change in size, and he did not add or remove gas as he heated. Alright, so after Amotin, we have Charles's law. That's how you remember how to spell it. Wasn't kidding. Charles's law. And so he looks at the relationship between volume and temperature. He's like, that Amotin, he did good work with pressure, but I feel like volume is just not understood well enough. So he stepped into the fray, and he got Charles's law. And if you think I'm making fun of these laws, wait till you see the last one. Oh boy. Whew. And it's someone who's already got his name all over something too. That's the worst part. Where's my law? Where's Joachim's law? I want a law too. Like, I don't know what it would be with gases. They kind of covered everything, but something, anything. All right. So Charles found. So he basically did the same thing as Amotin. He took gas and he heated it up, but this time instead of having like a solid, iron or brass or whatever metal he was using container, he basically used a balloon. And he heats it up and he goes, oh, the balloon got bigger or the balloon got smaller. So if the balloon gets bigger, it increased in volume. So you're allowing the gas to, instead of having it pressurized against the container walls and push against them harder, when it pushes harder, they just expand until it stops. So volume changes. And so when he heated up his special, flame-proof balloon or whatever, it doesn't really matter what it is, he found that the volume also increased. Some quality chemical education for you today, by the way. Who cares what they did? This is what they saw. Alright, and so again, temperature is proportional to volume. You increase temperature, the gas is going to take up more space. They're going to spread out more. Alright? And again, this time instead of a fixed volume, it was a fixed pressure. Which, hey, our atmosphere is pretty good at doing, so that's not bad. And again, you're not adding or removing gas particles. So, next, there's 4 of these, by the way. So we're halfway there. Boyle's law. I'm not real big on calling these out by name either, but they dedicated their lives to the study of gases and gas-like behaviors. These are real gas men right here, and so by golly, who am I to not give them their due and write their name on their laws? So he looked at volume and pressure. Okay, so literally, by the way, literally what that means. So Boyle was basically just blowing up birthday balloons. Just think about that. That's what he did. He's like, I increase pressure, and the volume increases. I blow into the balloon, I apply a pressure, and it inflates. All right. Not really. That's not really what they did, because that's actually adding particles. But compressing gases. You compress a gas, you cut its volume in half, so you have something like a cylinder that the gas can't slide by, but you can push the cylinder up or go down. Like a gas cylinder that you might have for holding the hatch open in your trunk or something like that. That's what Boyle worked with. And so he found that as volume decreased, so if you compress the gas, that would cause pressure to go up. So something different for a change. So volume was proportional to 1 over P, or they were inversely proportional. If one went up, the other went down, or if it went down, the other went up. They did the opposite, whereas before it was up, up, down, down. Everything was nicely paired. Now you get this weird result. You're like, okay. Well, if you think about it, it kind of makes sense. You push the gas down, it's going to push back. That's what it does, right? And air brakes wouldn't work without it. So, to do this, held temperature constant, and number of gas particles. Okay, now we're on to the guy who actually basically literally did just inflate balloons. And you're going to know his name. Because, of all the things, like I wish I had the dumbest gas law. I'm just so jealous. Avogadro's law. Okay, so Avogadro looks at the number of moles of gas, or the number of particles of gas, and volume, and he comes to the striking conclusion, make sure you're sitting down for this, that more gas particles will take up, wait for it, more space. That's right. More gas particles require more space. Avogadro did that. He didn't even do it by studying gases. He just ended up having too many kids and just figured it out because all of a sudden he couldn't get around his own house without stepping on a Lego or something. No, he actually studied molecules, I think. Who knows? Maybe someone should write a book about it someday. Alright, so again, number of moles of gas increase, the volume increases. So these are directly proportional. And so, maybe these other ones, you work with gases, you get familiar with it. This one is just so blatantly obvious, and somehow it was the last one that was like all the hard ones were taken, all these hard laws were taken here, these relationships that were more difficult to study, and then Avogadro just inflates a birthday balloon and goes, name it after me. I put more gas in the balloon, and it gets bigger. But not exactly. He said it in Italian, but basically, yeah. So, and to do this, fixed pressure and temperature. So he didn't let pressure or temperature change. So you're isolating variables, right? Okay, so you're going to be like, oh my god, those 4 laws, what's going on, right? Well, we can put them all together. Their powers combined are the ideal gas law. Now here's why I don't stress those laws too much. Because our ideal gas law of PV equals nRT, PivNert, or I worked with a guy who called it pervertNert, and is one of the highlights of my teaching career, to be in a room while a 70-year-old man addresses an entire audience of college students and says pervertNert approximately 75 times in an hour. So, I continue the tradition by mentioning the story Not because it gives me an excuse to also say pervert nerd, but because it's a good story. And I'm just going to say Pivner. PV equals nRT. Alright, so if pressure goes up, temperature goes up. Well, both sides have to remain equal. So if pressure goes up, this doesn't change, this doesn't change. We'll talk about that in a minute, but it doesn't change ever. Temperature's got to go up to compensate. Both sides have to stay equal. This one goes up, that one has to match it. Same with volume and temperature. Volume, if temperature goes up, volume has to go up to match it. Now if pressure goes up, volume has to go down to compensate because there's nothing changing on this side. If number of moles goes up, volume goes up as well. So all the relationships are there. So that's why I don't stress these laws too much. These are all just gaining understanding to this right here. And so we have our pressure, our volume, our number of moles of gas, our temperature, which is in Kelvin. Very important to remember that. And then we got this little fellow over here. It's a constant. So what do we call it? How about the ideal gas constant? How about that? I think everyone will know what the ideal gas law constant is and when to use it. We're going to talk about that in a minute. So you've got a constant because it turns out P times V does not exactly equal N times T. You need a little bit of a kind of a fudge factor in there, something to kind of like get the numbers to line up. It's also known as the universal gas law constant, so in theory in some other universe I guess it's a different number, but that's not our problem because we're in this universe. So PV equals nRT. So there's 4 variables and then a constant to make everything fit together. That's what we have. And so we can do calculations with this, by the way, which we'll do in a little bit. So let's talk about that ideal gas law constant R. Alright, by the way, it's a pirate's favorite constant, just so you know. It's the only one that's not like a C or a K, as he'll see later on. There's so many, there's like CS and CF. So you have to put subscripts on them. And then a lot of K's as well. But pirates love the gas law constant R. Alright. I've been way too busy moving, I guess. If I'm making I never make pirate jokes. What's wrong with me? I think it's the low humidity. We need more water in our air here. That's the problem, clearly. So, it has units that are going to be based on the structure here. So it's going to be a unit of pressure times a unit of volume divided by moles times Kelvin. Alright? So volume will tend to be in liters. We'll talk about this right here. Pressure is a wild card per mole Kelvin. And it's just to get all the pieces to fit together. Alright, so per mole Kelvin cancels out the right hand side stuff. And then liters atmospheres cancels out the left hand stuff. Or, I said atmospheres. It's not always atmospheres. Unit of pressure. So what that means is because there's a bajillion units of pressure, there's a bajillion options for R. But again, we only care about 2 units of pressure, so we're only going to care about 2 values of R. Well, there's going to be a third one that creeps up later that doesn't have a unit of pressure in it. Because pressure times volume also equals energy, but don't worry about that. So, R equals 0.08206 liters atmospheres per mole Kelvin. R also is equal to 62.363 millimeters of mercury times liters, or you can flip it, whatever, times moles Kelvin. Okay? So remember, we only care about millimeters of mercury or atmospheres, and so just depending on what your unit of pressure is in the problem, use one of these values of R. You can go on Wikipedia, and there's literally just an entire list of different values of R. Like, what if it's, PSI times gallons? You start switching in different units for volume as well. So, these are technically the same value, it's just different units. It's like from here to Tucson is, oh god, I don't even know. It's okay. We'll play the. It's more than 0 and less than 1,000 miles. It's somewhere in there. So we'll say 150. I don't know. I haven't paid the drive. But it's also some number of kilometers. It's the same distance. It's just what unit are we talking about it in? Or it could be, a certain number of feet. See, this was easy in Oregon because I drove between Eugene and Portland at times. I knew the number, and everyone there, I get them to argue about how long it would take to drive there. I'm gonna have to drive to Tucson just for research for this class. Not Flagstaff though. I hear there's too many accidents on the way. All right, 2 of you got that joke, I'm sure. I hope that. I mean, am I hoping for highway accidents now? What have I become? All right, so. These are the values we use in calculations. So let's talk about actually solving ideal gas law problems now. Alright. There's 2 flavors of problems I can throw at you. Alright. The first type of problem. Alright, so we've got PV equals nRT. That's our ideal gas law. I give you every variable but one. Alright. Guess what you have to do for that last variable? You solve for it. Okay? So let's do an example of this. So basically, it's like I tell you pressure, I tell you volume, I tell you number of moles, you solve for temperature. Or maybe I tell you volume, number of moles, and temperature, you solve for pressure. So there's 4 variables. I got to tell you 3 out of 4 to do this. All right? I'm giving you a big old peek behind the curtain on these types of problems. Like I'm just giving away everything here. All right? So it's just you got to figure out what do you know, what don't you know, solve for what you don't know. Pretty straightforward, right? So, an example of one of these problems would be something like, what is the volume? Of exactly 1 mole of gas at standard temperature and pressure? Ho ho! I threw you a curveball. You didn't think it'd be so easy, would you? Alright, so that's standard temperature and pressure. That is 273.15 Kelvin and 1 atmosphere. Basically about lab conditions. A little chilly. I mean, lab in a freezer, but whatever. So those are standard temperature and pressure. Okay? So I've given you pressure, I've given you temperature. Now that I've defined what STP is, it's fair game for homework, quiz, problems, all that stuff. All right. It's even a whole section in your book just to tell you this. Right here, look at that. That's a whole section in your book in like 1 line. Not even a full line, like a third of a line. Go me. All right. So we got to figure out the volume. All right. So how many liters is this? All right. So we just go like, oh, okay. Well, PV equals nRT, and I'll break it down a little bit here. Do we know P? Yeah, it's 1 atmosphere. And these are exact. We assume exactly standard temperature and pressure. Do we know volume? No, I don't know volume. I'm going to put a question mark there. Do we know N? Yeah. Yeah. 1 mole. Exactly. All right. Do we know R? Well, yeah. Do we know which one we want to use? We want to use the one with atmospheres, right? And so we want this one right here. If we had millimeters of mercury, we'd use this one. But this is our guy right here. This is the one. All right. So it is 0.08206 liters, atmospheres, moles, Kelvin. Very important you write those units, by the way. Otherwise, you might have the wrong value of R, or you might have it upside down or something. You don't know. All right. And do we know temperature? Yeah. 273.15. It's the standard temperature, don't you know? Alright, and so we need to solve for V. To do that, we just divide both sides by P. So V equals nRT over P. Look at that, doing math with letters like some sort of brain genius. Okay. Now I plug in my numbers and I solve. The beauty of this problem is there's a couple ones, which is just less writing. Alright, we got 1 mole. That's our N, right? We identified that. 0.08206 liters. I'm going to make this fit on the page. Atmospheres, moles, Kelvin. Alright. Times temperature. Alright. 273.15 Kelvin. Again, I'm just putting the numbers, and I'm going to divide all of this by 1 atmosphere. Alright. Okay. So, I just go 1 times 0.08206 times 273.15 divided by 1. And I get 22.4 liters. Okay, so I think the book actually does this exact problem. So why did I do the exact problem as the book? Because I didn't feel like writing my own, obviously. No, there's another reason. This is a good number to keep in mind. Alright? So, 1 mole of gas at STP equals 22.4 liters. Alright? So, if you have 2 moles of gas, you're looking at about 44, 45 liters. If you double the temperature, you're looking at 42, 45 liters. You double the pressure, you're looking at about half. You're looking like 11. So it's just a good mental marker to kind of help build some instinct. So a mole of gas at room-ish temperature and pressure takes up a lot of space, right? It takes up a lot of space. And so a couple pitfalls to look out for when you do these problems. One, make sure you know what variable you're looking for. Make sure your ideal are pieces. Make sure your temperature is in Kelvin. Make sure you use the right flavor of R. Those are the 2 easiest mistakes to make here. So make sure all your units line up. Your atmospheres here mean you have atmospheres here. Millimeters of mercury here means you should have millimeters of mercury here. So on and so forth. And this should not be in Celsius. It should be in Kelvin. Alright? 0 needs to mean absolute 0, not the temperature water freezes at. So that's the story on the first type of problem. You just write your equation, plot your variables, and solve. Okay? The second type of equation is a little bit different, but it's the same sort of story. You're going to ID your variables and solve. Just a little bit different process. Alright. So, we have 1 or more variables that are changed from an initial condition, so you know where you start and you know how everything but one piece lands. Alright, so in the first problem we use PV equals nRT, the first type. This one's a little bit different. So you do P1 V1 over N1 R T1 equals P2 V2 over N2 R T2. So there's our before, or our initial, and then there's our after, or our final. Now I'm going to say right now there's a piece of this we can cross out immediately. The ideal gas law is the same on both ends, so we can actually cross that out. But what I did was I wrote something out that equaled 1. PV divided by nRT equals 1 for an ideal gas. That's what our ideal gas law says. So this equals 1, which equals this. Alright, so that's what we were doing there. So P1 V1 over N1 T1, P2 V2 over N2 T2. Anything that's kept the same, we can cancel. And how do we know? It just depends on the problem. Alright, so let's do an example here. So these can be tricky, by the way, because I don't have to tell you every single variable. I can just tell you one that changes and one that stays the same, or one that changes that both before and after, and one that you maybe only know the initial for, and you got to find out what it is after. So maybe volume is kept constant, number of moles are kept constant, and they cancel. But I don't have to tell you what they are. I just have to say they're kept constant. So if you try to go PV equals nRT on this type of problem, it can blow up horribly and go nowhere. So what does the problem of this style look like? Well, if a gas with an initial pressure, and that's a dead ringer, by the way, the word initial. If there's an initial, that means it changed. Alright, so you should start going, oh, it's probably this one. Let's see, so his initial pressure of 500.0 millimeters of mercury. So a little less than 1 atmosphere, about 2/3 of an atmosphere. Alright, but it is compressed, which means our volume is going to shrink from 20.0 liters to 7.50 liters. Alright, if you had to guess what I'm going to ask here, what do you think it is? I just gave you a pressure and 2 volumes. I think I'm going to ask for the second pressure. Alright, so what is its final pressure? Huh. Couldn't have said it better myself. Alright. So, you see this, you go, there's an initial, there's a final. Alright, we've got P1 V1 over N1 T1, or you can put the R in there if you want, but we talked about how you can cancel it right off the bat. We got our before, we got our after. Alright, do I know P1? That would be our initial pressure, so 500.0 millimeters Hg. Do I know anything else here? Well, I know V1 was 20.0 liters. And let's see, I didn't explicitly say it. I got a little bit sloppy, I guess, with this, but let's see. So we don't know P2, but we do know that V2 is 7.50 liters, and it doesn't look like, so if we're just compressing it, by the way, we can assume that we're not changing the number of moles of gas, and we're not changing the temperature either. And so we can cancel the temperatures, we can cancel the moles, and so we're left with this guy. We want to solve for P2, and so P2 is going to equal P1 V1 over V2. I just divide both sides by V2. Okay, a little bit of razzmatazz algebra there for you. And then I plug in my variables. All right, 500.0 millimeters of Hg times my volume, my initial volume, V1 of 20.0 liters. And then we're going to divide all that by 7.50 liters. Okay? Now, think about this for a second before we do the math. See if you're building those instincts. Do you expect the pressure to be higher or lower at the end here? Are we going to go up from 500, or are we going to go down from 500? So if we're decreasing the volume, remember our gas law says pressure is going to go up. So if you get a lower number, you goofed on the math somewhere. So there's ways to kind of check yourself. You might not know the exact number, but you should know it goes up above 500. And so when we do this calculation, we get 1,330 millimeters of mercury. And so there's nothing obviously wrong with that. So it looks good to me. It's above 500. We're in good shape. So you could have more variables change, but you'll notice I never defined what N and T were at any point, and I didn't have to. I should have made a note that they did not change. I should have said with constant, without changing the number of moles of gas and a constant temperature. So I apologize there. But you won't see numbers for them. And so that's, if there's missing pieces, this is your equation right here. Okay, so one last thing to talk about in this video. It's been a lot, I know. Whew, it's already 30 minutes. But we'll get on to stoichiometry before you know it. Don't worry. Now you never want the video to end, do you? Alright, gas density. So we can use the ideal gas law equation to rewrite the formula for the density of a gas. And we're going to do that real quick here. So remember that density equals mass over volume. How much stuff and how much space, right? And it's a property of matter that is distinct to every compound type of, so like gold will have a set mass versus aluminum. So, so you can use it to verify a substance. It does vary with temperature though. Alright, now PV equals nRT. We've got volume, that's nice. We don't have mass. So how do we get mass? Well, we're going to bring another equation into it. The number of moles times the molar mass, so mu is short for molar mass, equals mass, right? So this is grams per mole, number of moles. You've done this calculation so many times. So it's just dressed up with letters, some of which aren't even in the English alphabet. So that's cool. Alright, so we can rearrange this and we can get N equals M over mu. Again, a calculation you've done a bunch. So this is just taking molar mass and flipping it basically, and that gets you number of moles. We're going to substitute in here. So we get PV equals M over mu, because we're just subbing for N here. So if N equals M over mu, we can do that, times RT. Alright. And what we want to do is we want to get mass divided by volume and get everything away from it. Okay? So that means that PV times mu over RT is equal to mass. I just divided by MRT. Or I'm sorry, RT over mu. So I got M by itself. So I multiply by mu, I divide by RT, I get here. Now I'm going to divide by V, and I get P mu over RT equals M over V, which is our density, right? So that's the equation for the density of a gas. Alright, so there's a couple things we can talk about here. So, it depends on mu. So heavier gas particles are going to give us a larger density, which makes sense, because if there's an equal number of particles, but they're all twice as heavy as the particles over here, well, this is going to be heavier. It's going to be the same volume, but twice the mass. So each particle getting heavier gives us a higher density because it's more mass in the same unit of volume. So heavier gas particles basically, so an increase in mu equals an increase in density. Alright? What else are we dependent on? Pressure. Okay? So if pressure goes up, our density goes up. Why is that? Well, if pressure goes up, it means we probably shrunk our volume, right? We compressed it. And so it's in a smaller volume, so we're accounting for that. And so it has a higher density. Alright. So an increase in pressure equals an increase in density, because an increase in pressure equals a decrease in volume. It's just kind of hidden, right? The molecules are packed more closely together in a smaller space. It is also dependent on temperature. So if we decrease the temperature, it's inversely proportional. So if we make something colder, it's going to become more dense. Because again, if you cool a gas, its volume, if you allow it, will shrink, and its density will go up. Alright, and so you can think of like hot air rises. So this is how hot air balloons work. The hot air is less dense than the colder air around it, and that allows it to have lift and work. And conversely, cold air sinks. So, for example, just 2 nights ago, I went walking through a park here, and the power of irrigation, man, it was unreal. I walked. They clearly designed it for this, because I like walked into like a lowered part of the park, and I swear the temperature dropped like 10 degrees immediately, because it was like a pocket of cold air that was just sitting in there, and it was cooled by the evaporation of water from the irrigation system. So it was pretty slick. I don't know if all parks do that here. I haven't been to that many. There's just one in my neighborhood I went to. But it was dramatic. Like the second you went down into that gully, you just felt the cold air. It was unreal. And that's because cold air sinks. Because lower temperature equals higher density. Higher density stuff sinks. Lower density stuff rises. So that's what's happening. Alright, so that'll do it for this video. It was a bit of a beast. But, and by the way, we had a derivation at the end of it, so that naturally, if you had any brain cells that hadn't been microwaved yet, you're welcome. I took care of them, all cooked now. So, the main thing is not necessarily being able to go from point A to point B, but just understanding and being able to interpret this relationship for the density. Being able to do calculations with PV equals nRT, understand how to use the variables, how to identify what type of problem it is, how to solve it. Those are the big things. So you'll have some practice, on the practice sheet, obviously, but also there'll be plenty in the homework. And I suspect that these are very quizable things. So just a heads up on that. So next we are going to talk about gas stoichiometry. So out of the pan and into the fire, or whatever the saying is. I don't know. I'm getting pretty tired too. This is a long video. So our old friend stoichiometry is coming back. We can tack gas laws onto it and work on some problems there.